Welcome to this video on the application of calculus in backpropagation algorithms to train neural networks. Now, that sounds like a pretty complicated subject, but I'm pretty sure calculus students should be able to understand this. First of all, what is a neural network? This is a diagram of a simple neural network, and each of these circles here is a neuron, and each neuron can hold a value from 0 to 1. Between each of these neurons, there are connections, as you can see with the arrows, that are actually really hard to see. And in the neural networks that we'll be looking at, all of these connections connect all of the neurons from the previous layer to the next layer. And that means that this neuron is going to connect here, 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 and here. This is going to connect to all of these, and just so on throughout the entire thing. And each one of these connections holds a value called a weight. Remember that for later. Let's imagine our neural network as a function. When imagining it like this, we can think of all the inputs as our independent variables. We'll call them x. What's actually happening in here, in the hidden layers and these weights and connections, is going to be f, our actual function. And the values of the output layer is going to be f of x. In the end, a neural network is really just a function that's run on a computer that can be written in math terms. These, of course, are not the specific math terms, just symbolic representations of how a neural network functions, but I'll get to the specifics soon. Before that, I'm going to show you an animation of how a neural network runs. This network is a little bit different than the last one. Like the other one, we have 4 layers of neurons, but this time we have 4 inputs and 3 outputs. As you can see, we input 4 values into the 4 input neurons. As I said before, a neuron holds a value from 0 to 1. Our input is simply setting that value. In this case, values are represented by the saturation of this green color, white being 0 and green being 1. To describe what's happening in the animation in layman terms, the values of the input layer are being passed to the second layer through all the connections, with the weights of each connection affecting how much each of the neurons in the input layer is going to affect the layer ahead. The new values of the second layer are going to pass to the third and then the fourth layer, which is our output layer. That may have been confusing, so now I'm going to lay out the exact equation we use to calculate just one neuron's value, based on the layer behind it. Okay, so this is the equation, and this is the neuron we're trying to calculate the new value for. These are the neurons in the layer behind it. So if this is the new neuron that we're trying to find the values for, these 4 would be the ones over here. Networks can have differing amounts of neurons per layer, so we're going to classify each of these neuron values as x of some value n. So x1, x2, blah blah blah, xn. Each neuron is going to be connected to the gray neuron and have a weight attached to that connection. As I said before, the new neuron's value is based on the value of the input neuron as well as the weight. That's where this summation comes into play. Ignoring everything else, this summation is essentially adding up the value of each neuron times the value of its weight. And this can be seen down here. And I just have a dot 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 to show that it continues on. Value times weight, plus value times weight, plus value times weight. And that's our summation. Now I'm going to introduce a new value called bias. Everyone has bias, and so do neurons. The value of a neuron is going to be affected by its bias. Essentially, we just add up the bias of the gray neuron to the summation. The last step in determining a neuron's value is running what we just calculated into a function. Here it's labeled f, but the name of this function is sigmoid. Sigmoid stands for S-shaped curve, and our sigmoid is going to be the function shown here, 1 over 1 plus e to the negative x. The reason why we do this is because, as I said before, a neuron can only have a value from 0 to 1, and the sigmoid will essentially squish that into that parameter for us. Negative numbers getting closer to 0 and positive numbers getting closer to 1. So yeah, that's our final value. And something to keep in mind for later is that just the summation plus b is going to be classified as the net of the neuron. But after you plug it through the sigmoid, that's called the out. That's going to be important when calculating backpropagation later. Keep in mind that this calculation happens like this through each layer, where neurons don't really have values until they are given them by the previous layer, which of course originates from our input. Okay, so that's a lot of context, but we still haven't quite made it to the calculus. First, I need to explain to you what cost is. In order to train our neural network to create the output we want, we need to quantify how good or bad it's doing its job. That's where the cost function comes into play. C is the cost, and it is our numeric representation of how bad our network is behaving. The higher the cost, the worse it is. The lower the cost, the better. To compute cost, we're going to need an actual output of our function, which is what we would have calculated before, and we're also going to need an expected output. When training neural networks, you need to have an input and an expected output. For example, if you are making a dog recognizing network, the input might be an image, and the expected output would be if there was a dog in that image. Humans would sift through images and mark if there was a dog in the image, and then the information would be used by the network to calculate the cost in the form of the expected output. So what we do to calculate the cost of the network is take a summation of each neuron compared to its expected output, we square it, and then divide it by the amount of outputs we have to find the average cost. With cost explained, we will finally move on to backpropagation. Backpropagation is the process in which we go backwards through the network, adjusting each weight and bias to lower the cost function in an optimal manner. Let's perform backpropagation on this simple network. I stands for input, H stands for hidden, and O stands for output, and those are 3 different layers. The B's beneath are the biases, and just for simplicity, H1 and H2 will have the same bias, and O1 and O2 will have the same bias. Let's say that these are the values of the network. 0.5 and 0.1 are the inputs. 0.01 and 0.99 are expected output values. And the rest of the weights and biases are pretty much just filled in randomly, like a neural network would be when you initialize it. I did the math on screen using our formula from earlier to get the values of H1 and H2, and then used those values to calculate our actual output values for O1 and O2, or that are right here. I'm going to be using these values later in the video to plug in to our equations, and if you ever get lost or don't know where a value comes from, or forget what one of these is, just refer back to this slide. Okay, so now that we have all the values that we need, I'll explain the specifics of what our aim is when backpropagating this network. We want to find how much each one of these weights and biases affects our cost function, so that we can adjust them proportionally to lower it. Adjusting them proportionally to their effect on the cost function is important, because some weights and biases hold more power than others. And adjusting them all by the same amount, but in the right direction, would completely throw everything out of whack. Normally we would go through and adjust every single weight and bias, but for our example, we're only going to find how W1 affects the cost. Writing out how W1 affects the cost function in calculus terms is as such: dc over dW1. A really intuitive way to think of this expression is the ratio of how an infinitely small nudge to W1 would change our cost value divided by that infinitely small nudge to W1. To find the actual value of dcost over dW1, we're going to split it up into smaller derivatives. So these are the different steps to find how dW1 affects cost. And by finding how, let's say, W1 affects net, and then how net affects out, when we multiply those two values, we will find how W1 affects out. So let's write down all these new derivatives. This first one is going to be how the out of the H1 neuron is going to affect the total cost of the function. D out of H1 over D net of H1 is going to be how the net of the H1 neuron affects the out of the H1 neuron. And then D net H1 over dW1 is going to be how W1 affects the net of the neuron. Remember that our net is just the bias plus the summation, and our out is after we plug it through the sigmoid. Okay, so let's focus in on one of these expressions. For now, we're going to do dcost over d out of H1. So as I said before, this expression is calculating how out of the H1 neuron is going to affect our total cost of the entire network. This is our formula for cost. And if we actually, instead of like doing the summation, if we convert it into like an algebraic terms, then we get this. By the way, O1 exp is a symbol I'm using for y prime, which is essentially our expected output for the function. So we can then split this up into two different functions that only are affected by each of these neurons. So cost of O1 only has variables that come from this neuron. Cost of O2 only has variables that come from this neuron, and when we add them together, they equal cost. This means that we can split our expression into two. We can have cost of O1 over out of H1 plus cost of O2 over out of H1. So let's once again focus in on only one of these terms. We'll do cost of O1, and this term can also be split up into three different terms. The three different terms are out of H1 to net of O1, net of O1 to out of O1, and out of O1 to cost of O1. And here I have everything numbered so you can see which ones are related to each other. These are the equations that are related to each of these. So we're going to find the derivative using these three equations. I don't think I have to walk you through these derivatives. They're pretty easy, especially the first one. We get these three derivatives for each of them, and if we just plug in the values that we found before, we get these three values. So now just plugging all those values into our equation, we get that dc01 over d out h1 is equal to this value right here. Stepping back, we need to remember that we're trying to find how out affects the total cost. So we also need to do this with the cost of the second neuron. But just for simplicity's sake, since you already saw the process of the first one, it's the exact same, and we'll just grab that value here out of thin air. I did the calculations, trust me, and move on. So now when we add these two values together, we get our value for how the cost function is affected by out of H1. Okay, so that's one of them done. We still have two more to go. Luckily, these two are a lot easier. So yeah, let's focus on d out H1 over d net H1. This derivative is going to be describing how net affects out. It's pretty dang simple. If we get our relating function, it's just that sigmoid again, and we do the same exact derivative to find that the value of this is 0.241. So nice, we have the second. Time to grab the third. As a reminder, this third value is how W1 affects net of H1. So if we find our relating function, which is just the summation plus b, we can do the derivative, and it just turns out to be I1, and we get 0.05. So now we calculated all our values, we have everything together, and we get our final answer as this tiny little number. So this is the value of how the W1 weight affects the total cost of the function. Well, how do we actually use that and apply it to making the cost lower? Well, if W1 plus is our new value for W1, we're going to take W1 and subtract it by a learning rate. And a learning rate is just an amount set by the programmer or whoever that's going to affect how fast or slow it learns. And the reason you want a learning rate is so you don't overshoot where you're trying to go. If it's too high, you can overshoot, but if it's too low, it's going to take forever. So you need it to be adjustable. So yeah, we do the calculations here, and our new value for W1 plus is 0.149. Hooray, you followed me through backpropagation, but a computer would be doing this hundreds of times in a row. When given multiple training examples, a computer will actually run through all of them and not change its value until it's finished, like a batch of like a 1,000 or 1,000,000, and then it'll take the average change that it wants to make to like the weight or bias over those training examples, and then it will move it by that amount. So instead of just getting like the one training example, what it thinks would be good for the function, we're seeing overall what would be best for the neural network to make it better. And this would happen simultaneously over all the weights and the biases. So hopefully you now understand.
Chandler.
Huh?
Chandler, I'm very disappointed in you.
What
This video has gone on for 15 minutes and you haven't done a single derivative.
I mean, I did.
Shut up. Because you won't, I'll show everyone how to do the derivative of sigmoid.
You really don't have to do that.
Okay, First, we're going to convert this fraction into an exponent. And then we're going to use the power rule. And then we're going to multiply. Oh, never mind. Don't forget the chain rule. Okay, so now we have the derivative, but there's a simpler way to write it. Okay, then we multiply it all together like this. We split it into these two fractions. We add 1 and subtract 1 right here, and then separate them again. We replace this fraction with 1, and then look, we can replace these two fractions with the original function, and we get the derivatives as sigmoid of x times 1 minus sigmoid of x. I know you looked that up, Chandler. You suck at algebra. I would leave right now, but I really want to sing a song for the calculus class. This one goes out to Adrian and all my other good calculus students. As I walk through the valley of the shadow of death, I take a look at my life and realize there's nothing left. Cause I've been blasting and laughing so long that even my mama thinks that my mind is young. But I ain't never crossed a man that didn't deserve it. Me be treated like a punk, you know that's unheard of. You better watch your talking and where you're walking, or you and your homies might be lying in chalk. I really hate to trip, but I gotta loke. As I croak, I see myself in the abyss of smoke. Fool, I'm the type of G the little homies wanna be. On my knees in the night, saying prayers in the street light.